All right, thank you, Alicia. It is my pleasure to introduce today's JQI speaker, Philippe Joyez from Quantronics Group. This group is a part of a French Department of Energy, and it is quite notorious for their research on macroscopic quantum effects in superconductors, including the implementation of the the first functional superconducting qubits, quantronium. And Philippe is, I know Philippe's work starting from his thesis, which I actually recommended to all students who want to learn about modern Josephson effect. And since then, he worked on a number of topics in superconductivity. Another one that is quite relevant for JQI is his work on Andreev bound states in mesoscopic junctions. He did really the first experiment where these states were energy resolved and modulated by the phase difference. It was, I guess, was very important for the development of the Majorana physics, so to say. And these days he's going to talk about a politically inspired topic, which is actually very old. It's over 30 years old, I think, of how dissipative quantum phase transitions really work in superconductors. I would just say briefly that there was this a very speculative prediction that a Josephson junction doesn't really know whether it's a superconductor or an insulator unless you decide what other circuit elements you connect to it. And in particularly in case of connecting it to a resistor, the answer was that if this resistance is very large, the junction all of a sudden becomes an insulator. While it's very low, it becomes a superconductor. And it's very hard to reconcile this prediction, but it's quite fundamental. It's linked to many other topics in condensed matter physics, actually, to quantum impurity models. And Philippe is going to talk about it today, about his recent experiment and theory work. Okay, Philippe, welcome to JQI. Looking forward to your talk.
Okay, thank you, Vlad, for a nice introduction. So, yes, the title is a little bit provocative or misleading. The real title is about the absence of a dissipative quantum phase transition for Josephson junction. We could say that the subject of the presentation is to show that despite all the polls predicting the opposite, a resistor cannot drive the Josephson junction to an insulating state. So I will first introduce the main character of this drama, the Josephson junction, and explain how it works. Then I will describe the phase transition that was predicted, how we validate it experimentally, and how we resolve the discrepancy between the prediction and the experiment. Okay, so I have prepared this presentation so that it is accessible to non-specialists. However, the things I explain are not clear, or if you feel that you need more details, do not hesitate to ask questions and to interact. So first, this Josephson junction. This is the superhero of this story because it has an S, you see. So it's just a tunnel junction. It means that it's a thin insulating layer separating two pieces of superconductor, and through which electrons can tunnel. Okay, so this is the insulating layer. And a common way to fabricate such a device is to make a suspended mask here by electron beam lithography, and to evaporate metal under two different angles with an oxidation step in between. So you get two images of the mask here, and at the overlap here, you form a tunnel junction with the outside forming the tunnel barrier, and that's a SEM picture of such a tunnel junction. So that's how we make them in our lab. And now, if you measure the IV characteristic of such a tunnel junction, that's a real experiment, that's what you obtain. So there are two striking features in this IV characteristic. First, at zero voltage here, you notice a vertical branch, so a zero voltage supercurrent branch. And then at finite voltage, below the gap of the superconductor here, in fact, there is no DC current flowing through the junction. And above that gap voltage, you recover a linear IV characteristic of a normal state tunnel junction. Josephson was the first to give the electrical equations for this component. These electrical equations explain these features that we see on the IV characteristic. So from an electrical point of view, the Josephson junction is just a two-terminal component. And we know that in a classical circuit, we describe the state of a two-terminal component by the voltage drop across it and the current that is flowing through it. And then there is a constitutive relation linking the two, for instance, it's Ohm laws in a resistor. Now, in quantum circuits, we generalize this, but the voltage and the current become operators. However, it's more convenient to describe the state of a quantum two-terminal component in terms of the flux and the charge, which are simply the time integral of the voltage and the time integral of the current flowing through the device. Because these two quantities are quantum conjugate, and you can think of them as the position and the momentum of the quantum particle. So there is a capacity behavior and a pure tunnel element, and the charge that is flowing through the device will divide. So part of it will flow through the tunnel element, and this will be an integer number of Cooper pairs, so it's a spectrum in integer numbers, and the rest is going to charge the capacitor. So there are two energies that are associated to this. One is the electrostatic charging energy of the capacitor, so Q squared over 2C. And here, EC is the energy scale of 1 Cooper pair on the capacitor. And there is an energy also associated to the tunneling of Cooper pairs through the tunnel element. And for this, the energy will be associated to hopping between a charge state and an adjacent charge state. So this is a translation operator for the charges, and you can write it as the exponential of the conjugate variable, the phase across the junction. And if you take the two terms, then it makes a cosine. So there is an energy minus EJ cos phi. It has a minimum at zero phase that describes tunneling through the Josephson element. And you can see this minus EJ cos phi as a block band for this tie binding model of a discrete charge state. Okay, so now from these energies, we can more or less directly get the electrical behavior of the Josephson junction, and that's what Josephson does. So if we go back to our junction connected to a source here, the DC current that is flowing through the device can only flow through the tunnel element. So the current will be given by the time derivative of the charge going through the tunnel element, and this you get by taking the derivative of the energy with respect to the conjugate variable. So it gives us a sinusoidal dependence on the phase difference, and the prefactor is called the critical current of the junction, and this is known as the first Josephson relation. The second Josephson relation is just the link between the voltage and the phase, and this has nothing to do with tunneling itself. It's just the way we have defined this phase. But it's still called the Josephson relation because it was the first to write it down. So from these equations, we can, oh yes, and I will also say now that in a low impedance circuit here, such as this one, where you use a voltage source, the phase can be considered as a merely classical variable, so it has no quantum fluctuations. So from these equations, we can understand the IV characteristic that I was showing a little bit earlier. And since this supercurrent branch here, so we have zero voltage, so it means that the phase is static, and this allows a current to flow in the junction between plus and minus I0. So that's the maximum value here that we see. And I'm not showing this, but this critical current of the junction is proportional to the gap of the superconductor and the normal state conductance, the inverse of the resistance, and this slope here at high voltage. Now, at finite voltage here in this region, so we have a finite voltage, which means that the phase is evolving linearly in time. And if we put back this linear dependence of the phase in the first Josephson relation, we get that the current is oscillating in time with a frequency that is given by the voltage and this ratio of fundamental constants. So we have a Josephson junction, which is an exact frequency to voltage converter with a very high conversion ratio here. And in fact, this converter here can also be used in reverse. That is, if you send a high frequency signal to the junction will lock onto that signal and deliver a fixed voltage. And actually, this is used in both standards. So you can make arrays of Josephson junctions here, and by sending microwave to this array, you can generate a very precise volt standard, and that's used to calibrate voltmeters. And these devices are independent, so they rely only on the Planck constant and the charge of the electron. So they are independent of the material you use, of the layout of the design you circuit. And in fact, among different labs in the world, the reproducibility of such experiments is excellent, 10 to the minus 9. And this has helped rebasing the SI system on the fundamental constant last year.
So I'd like to point out to our division chief, Jerry Fitzpatrick, that without NIST, this work would not be possible. Would you agree with that, Philippe?
Yeah, you're doing an excellent job, of course. Okay, so let's go back. So these are arrays of Josephson junctions. Let's go back to our single Josephson junction and try to compare it to a more familiar electronic component. So, in fact, our pure tunnel element here, with this energy minus J cos phi here, you can see it as a nonlinear inductor. Okay, so we have this energy minus J cos phi, and in the first minimum of the cosine here, you can approximate it by a parabola if you want, and this parabola would be the energy of an inductor. Okay, so phi squared over 2L, which is the energy that is stored in an inductor. And so the L is the inverse of the curvature of the parabola, and we can generalize by taking the curvature of our cosine that gives a generalized nonlinear inductance of the Josephson element. So if we take into account also the capacitive behavior of the junction, our junction here, by itself, it makes a nonlinear oscillator. Okay, so here in blue we would have a linear oscillator made of a linear inductor and a capacitor, so it's just an harmonic oscillator. Here, our junction is a nonlinear inductance in parallel with the capacitor, so it's a nonlinear resonator, and it has a non-harmonic spectrum. Okay, so the levels of this quantum device are not equidistant, and this allows you to use them as qubits. In fact, so if you restrict to these two lower energy states, you can use this as a two-level system and make a qubit out of it. So by analogy to the harmonic oscillator, you can work out what are the zero-point fluctuation in the ground state and phase or the charge, and you can relate them to the effective impedance of the circuit, that is the square root of the ratio of the effective inductance to the capacitance, the square root of EC over EJ, the two energy scales that define a junction. And these zero-point fluctuations are given by the ratio of this impedance to the quantum of resistance, H over 4 squared, which is about 6.5 kilos. Now, the anharmonicity of the device here depends on the ratio EG over EC, and at very large EG over EC, it goes to almost zero. That means that the nonlinear oscillator becomes nearly an harmonic oscillator. So this Josephson junction by itself is, like I said, it can be considered as a qubit, and this it makes, in fact, a whole family of superconducting qubits that generically can be called the Cooper turbos. We have made some of them in our lab in the last century, and that's how this nickname was coined. But nowadays, transmons are operating in the large EG over EC ratio and are the most successful qubits in use. Okay, so that's for the junction by itself. Now, what happens? What is the effect of dissipation on a Josephson junction? So what happens if we take our Josephson junction and connect a resistor to it? So classically, it's rather obvious what will happen. We have a nonlinear oscillator here, and the resistance will damp the oscillation of the nonlinear oscillator, and we can expect to have the quality factor of the oscillation that will be given by the resistance divided by the impedance of our nonlinear oscillator. Quantum mechanically, the effect of dissipation on the junction was first investigated at the beginning of the 90s by Caldera and Leggett, and they showed that any impedance in a given circuit could be decomposed in a series of LC circuits with varying, so equally spaced in frequency, but with varying impedance of these modes, such that they would reproduce the real part of the impedance that you want to model. So they wrote down what is called the Caldera and Leggett Hamiltonian for the junction coupled to a resistor. So we have this Hamiltonian of the bare junction, and the junction is coupled to this bath, this ensemble of harmonic oscillator in this way through the phase here. And they showed that Caldera and Leggett showed that this bath of harmonic oscillators implements diffuse dissipation. That is, you have a force that is proportional to the velocity of the phase, that is to the voltage, or the velocity of the charge, to the current, and that gives a dissipated power that is, as expected, R I square or D square over R. So if you take just a frequency independent impedance, which is a resistance, a pure resistor. So they, in fact, Caldera and Leggett were interested in modeling dissipation because they wanted to understand what was the effect of friction here on a phenomenon that is called macroscopic quantum tunneling. And this phenomenon occurs when you consider a Josephson junction, which is biased by a current source. So in this case, the cosine potential for the phase gets tilted by a linear term, which is proportional to the current source. Yeah. So you get a local minima in this potential, and you have quantum states that can reside in the local minimum, and they can tunnel under this potential barrier and escape here, so that in the end the junction has its phase that is evolving in time. So you end up in a voltage state for the junction. Here, if you are trapped in this metastable state, you are in a superconducting state. But if you wait long enough, this state can tunnel under the barrier, and you end up at a finite voltage. And this escape as a tunneling as a rate to occur that you can cast as the exponential of the energy barrier over the escape temperature, which is another way. So the escape temperature is another way to measure this tunneling rate. Caldera-Leggett predicted that if you connect a resistor here to the junction, it would reduce this tunneling rate. And in fact, this was clearly observed in experiments. So in this experiment, a few years later, data measurement of the escape rate showed that it was agreeing with no adjustable parameter with the prediction made by Caldera-Leggett for the reduction of the tunneling rate. This dash line would have been what would be measured if there was no resistance shunting the junction. So that was the initial motivation of Caldera-Leggett, and almost simultaneously, Schmid considered the problem of the diffusion of a quantum particle in a periodic potential submitted to a viscous force. And this prediction was refined shortly after by Joyez, and they came with a phase diagram for the system, which said that whatever the depth of the potential and the mass of the particle, there was a critical value for the friction that would make the ground state of the system being either localized in a way if the friction is strong enough, or delocalized like a block wave in the periodic potential. So both Schmid and Joyez realized that the Josephson junction would be a very good test bench for this prediction, and they said that people should observe as a function of the ratio E, and independently of the ratio EG over EC, that above a given value of the resistance, the particle would be localized in a way. So the phase localized in a way, I remind you, it's a superconducting state. And if you are below this inverse ratio, so that is, if the resistance is larger than the quantum of resistance, then the phase will be diffusing. So that corresponds to a voltage state. So the junction will be insulated. So that's a prediction for the ground state of the system. So this theoretical prediction dating from 83 was confirmed many times, and it's very widely accepted. I mean, this paper by Schmid has more than 400 citations. However, experimental tests are very few and not very convincing. So I will show you two of them. So this experiment by Yagi et al. In 1997. In this experiment, they made Josephson junction with a normal state resistance of 26 kilohms and junction, and they connected different resistance in parallel to the junction and measured the global resistance of this parallel combination as a function of temperature. And that's what they observed for different values of the resistance. And they concluded that for resistances that were above the quantum, okay, so they observed, they observed a slight increase of the resistance and then something like that seemed to saturate. And they concluded that this was an insulating state. And on the other hand, for lower value of the resistance, they concluded this is the superconducting state. But if you think of it, if the junction is insulating, then what you should measure at low temperature is only the value of the resistance here. So it should go to this value. And similarly for the orange trace, it should go to this value. And if the junction becomes superconducting, then it should go to 0. So it's not very convincing, but that's it. A couple of years later, Spentila and co-workers made another set of experiments. And they, in their case, they looked at the differential resistance of the junction as a function of the voltage, the differential resistance. And if the trace had a bump in the middle, they said it was an insulating junction. And if it had no bump, if it had a minimum at 0 volt, they said it was a superconducting junction. And they found that above a given value of the ratio EG/RC, their junction were, they would classify their junction as being superconducting, and they and junction with low EG/RC were rather having this insulating behavior. So their interpretation of observing this was that when EG/RC gets very large, the height of the potential here gets large, and which means that for tunneling through the junction, through this potential, the tunneling time will get very long, and the time it takes for the particle to diffuse in order to make this insulating state will get very large. So their interpretation of this is that they were only observing a metastable state, and that the ground state of the system would eventually be reached in a very long time that made it unobservable. And they came with some equations saying that the observable boundary for the phase transition was this continuous line. So you see, they needed to reinterpret the prediction in order for their experiment to agree with the prediction of the phase transition. So that's on the experimental side, but there are also some other problems right with the phase diagram itself, because it is conflicting with known limits of shunted junction. For instance, if you consider the R goes to infinity limit, so you take this value of the resistance to infinity, so that you can simply remove it from the circuit, then you are left with something that we know very well. It's a Cooper box. It's a superconducting qubit. So on this, and we know that superconducting qubits are superconducting. So we expect that the left axis on the diagram here should be painted green, so it's superconducting. Similarly, if we go to the large EG/EC ratio, we know that our junction will become nearly an harmonic oscillator, and a damped harmonic oscillator we know exactly how to solve, and we know there is no quantum phase transition, so it should be superconducting all along near the top axis here. Okay, so you see that this phase diagram is problematic with respect to simple limits that we know. Okay, so even though most people strongly believe that the prediction is okay, but it's not so obvious when you think of it in terms of simple cases, simple limits. And so that's something we wanted to clarify. So the thing we should ask now is how can we test for the presence or the absence of this quantum phase transition. Well, it turns out that there is a generic theory for quantum phase transition that you can find in this review here. So let me just say what is a quantum phase transition for people who don't know. The quantum phase transition is by definition a system in which at a given value of a parameter, the ground state of the system changes from one realization to another one. So it can be here an ordered state or a disordered state according to the value of that parameter. And the transition occurred at what is called the quantum critical point, QCP. But that's the ground state of the system. And the ground state is at 0 temperature, and experiments are only carried at a finite temperature. So what can you observe of this ground state transition at finite temperature? And this generic theory of quantum phase transition shows that at finite temperature, above the ground state, there is a quantum critical regime that develops in which you have universal scaling laws of the equilibrium properties of the system that appear. Sorry. So it means that if you start from a point in the disordered phase here and you raise the temperature, you will enter at some point this quantum critical regime in which you will find that equilibrium properties of the system follow universal power laws with temperature, and the exponent of these power laws are also calculable. You can predict them. So in our case, it means that if we take a Josephson junction in the insulating phase of the phase diagram here, and we raise the temperature, at some point we will enter this quantum critical phase, and we should observe that the linear response of the junction has a temperature power law dependence. So that's what we have tried to do in the experiment. So that's how we have measured the linear response of Josephson junction supposed to be in the insulating phase. So we have made on a chip a Josephson junction. In fact, we used two junctions in parallel. So this forms a squid, and a squid is a tunable Josephson junction. That is, by changing the flux in the loop here, you get a Josephson junction that has a Josephson energy that is modulated periodically with this flux in the loop. So it's just a trick to measure several values of Josephson coupling energy in a single experiment. That's the capacitance of these two junctions in parallel. On the chip, we have made a resistance here, but it's not directly connected in parallel with the junction, so that we can measure the current flowing through the junction. Right? So we open the circuit here and close it off chip in this bias. Okay, so the junction is in fact connected to the junction, but outside of the chip. So in this setup, we have here a microwave source that we attenuate. We send it on this very small capacitance, and this will behave as a current source at the frequency as reduced. So we inject some current here. This current will divide between this branch here and the resistance. And here at the output, the high frequency signal will go through the capacitor. We amplify it and we detect it. So by measuring the transmission through this system here, we can have an idea of what is the current going through the resistance or through the junction, and figure what is the linear response of the junction itself. So that's how this was made in reality on chip. So squid loop, the two junctions are here and here, the squid loop is here. It's connected to a chromium resistor, okay, and then this is made into a microwave transmission line so that we can send in our probe signal and measurement signal. We've made two different samples with these parameters here. So we have two different values of the resistance that were clearly on the insulating side. So we have two different values for EJ, for the maximum EJ of this junction that we could vary by changing the flux in this loop. And otherwise, the two chips were very similar. So we wanted to measure only a linear response of the junction. So for this, you want to restrict the phase excursion on the junction to be very small, so that you can make this parabolic expansion of the cosine. And this is okay. You can check with the parameters that are here that at 1 gigahertz, if the power that you have at the input of the chip is smaller than the minus 50 dBm, then you are in the linear response regime. Now, you also want to avoid Joule heating in the resistor, and this with the sample parameters that we have, we can knowing how electron heat up in a resistor, we can convince ourselves that the raise of the electronic temperature due to the Joule power that we deliver in the resistance can be kept below 1 milli-K if the input power is at minus 70 dBm as we used in experiment. And finally, if we take a frequency that is below the plasma frequency, that is the frequency of the ground state of our nonlinear oscillator here, then we can relate the S21, so that the transmission measured in this setup, to the linear response, the admittance of the junction through this formula. We have this coupling capacitance here. Z0 is the 50 ohm impedance of the microwave circuitry that is here, and R is our on-chip resistance. So we see that in this measurement, when the admittance, when the admittance of the junction increases, so when it gets more conductive, we expect to see a decrease in the transmission. Okay, so here are the measurements for our two devices. So on this panel, we show the measurement of S21, the modulus of the transmission in the experiment, as a function of temperature for different value of the flux in the squid loop, so modulating the EJ of the junction. And what we observe is that at low temperature, we have a saturation of transmission that is independent, that indicates that the junction remains superconducting, and we see no power law of the linear response. If we had a power law of the linear response, we would see all these lines converging to a given value. Power law dependence here. And we observe the same behavior in our two samples. So we can be confident that our junction is not becoming insulating. So it doesn't seem to be in a quantum critical regime that would exist if there was quantum phase transition. It's also consistent, I mean, not observing an insulating state here is also consistent with the the limits that I had introduced for the qubits at infinite resistance, where we expect superconducting state, and at large EQ over EC. So overall, what we observe is consistent with having no insulating phase for Josephson junction, the absence of this insulating phase. Okay, we observe in our experiment some striking behavior here, where there is a maximum of the admittance at intermediate temperature, and over here it's when the aluminum is becoming normal again. It's a critical temperature of the superconductor we are using. I want to show you that we are not the only one to conclude that Josephson junction in series with a large resistor is superconducting. Almost at the same time, Grimm and co-worker have measured the IV characteristic of a junction in series with a 32 kilo ohm resistor, and they have shown that at low current, it was behaving as a superconductor. Here, this is the load line of the resistor alone, so there is no voltage drop on the junction, superconducting. Okay, so we have intermediate conclusions for our experimental results. Okay, so our experiment shows no sign of insulating phase as T goes to 0, and is consistent with many other experiments. The qubits, the Grimm experiment, and so on. And not having this insulating phase would agree well with well-known simple theoretical limits. So one could ask, well, could the theory simply be wrong? Well, no, it's not that simple. Okay, so we have this prediction by Schmid and Joyez of quantum phase transition for a particle in the periodic potential with friction, and this this problem is in fact similar to another problem investigated by Kane and Fisher for a Tomonaga-Luttinger liquid with an impurity. So it's a 1D fermionic system here. And for this problem, Kane and Fisher showed that if the TLL is as an attractive interaction parameter, if the TLL as an attractive interaction parameter, then whatever the strength of the impurity you get at 0 temperature of perfect transmission, whereas if the TLL is repulsive, then you get whatever the value of the impurity potential, you get an insulating state that it cuts the TLL in 2 parts. Now this problem was mapped by Safi and Saller onto the quantum point contact in series with a resistor, but it's a mapping that is valid only for repulsive TLL. And the mapping goes this way: the interaction parameter of the TLL is mapped to 1 over 4 times the resistance of the resistance quantum. And this problem was investigated experimentally in great detail by people working not very far from here, and they observed very nicely the universal power laws. So it's an experimental check, and we can say that they have made a quantum simulator of this insulating phase here. So it's funny because when I started doing physics, the real stuff was the experiment, and the model could only be an approximate description of the experiment, but now it's the other thing, the other way around. The most important thing is the model, and the experiment is more or less a close implementation of the model. Okay, anyway, in our case, clearly our experiment is not a quantum simulator of the Schmid and Josephson prediction. But okay, so this experiment confirms the validity of the Schmid and Josephson prediction. So it cannot be completely wrong. Okay, so the prediction is still very solid. Okay. You cannot just throw it to the trash bin. So what's the reason for the disagreement? So one possibility is that we messed up the experiment, but in our experiment we observed that the junction is superconducting, and superconductivity is a rather fragile thing, and it's very unlikely to show up in a case where it should not be there. So it's very hard to argue that the experiment is showing superconductivity in a place where it should not be there. The other possibility is that the Caldera-Leggett Hamiltonian, it was used to make the prediction, does not properly describe a shunted Josephson junction. We know that it properly describes the effect of dissipation in the case of macroscopic quantum tunneling. So we will not go in this direction. The only thing that we can think of is that Schmid prediction does not strictly apply to Josephson junction, and we have to understand why this is so. So Schmid model is the Caldera and Leggett Hamiltonian that I've shown earlier. In this Hamiltonian, if you change the phase by 2 pi, here the value of the Hamiltonian is different. So this calls for using extended phase states, in fact, the different wells of the cosine potential are distinguishable. And it's very important to realize that the insulating phase was predicted assuming such kind of extended phase state, assuming that the different wells of the cosine are distinguishable. But we know this is inappropriate for qubits at least. And our experiment seems to show that it's also inappropriate for Josephson junction, shunted Josephson junction, because we don't observe this insulating state. The other way to model a Josephson junction coupled to an environment is this writing of the Hamiltonian, where the coupling of the junction through the harmonic oscillator back is rather made through the charge that has flown through the resistance. And in this case, you see that the Hamiltonian, in fact, is now invariant with respect to changing the well of the cosine. And this calls for using compact phase states, so that is a phase living on a circle. But you can also use an extended representation of compact phase state. Simply, in this case, the wave function of the junction will be the same in every well of the cosine potential. So here we have two different Hilbert spaces. Okay, it's not the same family of states that we consider. And we know that these compact phase states are appropriate to describe qubits, that is, shunted junction in the limit where the resistance goes to infinity. And we know that these qubits are superconducting. And by using a perturbation theory, we can argue that this description here is also valid for non-infinite resistance, unless a spontaneous symmetry breaking, that would be a decompactification, this breaking of this symmetry of the state occurs at some point. So we have two descriptions of the systems. It seems we have two families of states. However, we can show that these two Hamiltonians are related by a unitary transformation. And if you do things properly, in fact, any state of this kind can also be represented in this Hamiltonian, because doing the things properly means that you also need to transform the boundary conditions and the initial state of the system when you perform the unitary transformation. And then in this case, I mean, you can use either this Hamiltonian or this one. They are both equivalent for these families of state or these families of state. So nevertheless, we can conclude that compact or extended phase describe different physical systems because they don't have the same inverse space. And Schmid's prediction, Schmid quantum phase transition, only occurs with extended phase. It's not suitable for Josephson junction. Okay, so if we come back to this previous slide here, this prediction was the same as this one, because when you have the same effective action, in fact, you also use the same inverse state. The problem here is that this system is not in the same inverse space as this one. And by the way, these systems are normal state systems. They are not superconducting systems. So now we can think a little bit more at what we measured and what Schmid and other people predicted. So the linear response that we measure is the admittance of the junction, and it can be calculated using quantum mechanics as usual. And it has in fact two terms. It has one term that is the standard Kubo linear response formula, and one extra term that comes from the ground state of the system, and that gives us an inductive response. In fact, this I omega at the denominator here is the response of an inductor. And here, this average value here is the equilibrium reduced density matrix, taking the trace of the equilibrium reduced density matrix for the junction. So what Schmid and others calculated when they predicted their phase transition was the DC mobility of the system. This DC mobility, by definition, is the limit when you take the bias voltage to 0 of the DC current to the DC voltage. And if we use our formula, this corresponds to taking the real part of the admittance at 0 frequency. So this is a purely imaginary term. So this mobility only considers the Kubo term. It only considers dissipative conduction. And we see that here, since it's at 0 frequency, there may be a problem with taking the limit to 0 frequency, since here we have a diverging term, in fact, when we go to 0 frequency. And it's rather easy to convince oneself that the mobility is inappropriate to characterize transport properties in superconducting systems. Yes, I'm sorry. I don't right now. I'm getting lost, sorry. Okay, so for instance, if you consider an unsheltered junction, I've shown to you an experimental trace before, but theoretically it's very simple to predict what's the IV characteristic. Okay, you have the superconducting state and the AC Josephson state here, which has 0 DC current, but which is not an insulating state. But if you take this formula on the mobility, you would predict that the mobility is 0, and mobility 0 is what theorists say is an insulating system. So in the case of a shunted junction, now at so that's close to the supercurrent branch here on the supercurrent branch at low voltage. Okay, the IV characteristic of a junction here can sustain finite current at finite voltage because now the resistance can absorb the power that is delivered by the source. And in this case, you have two contributions to the IV characteristic of the junction. You have one contribution that comes from the Kubo term here, and one contribution that comes from the inductive response. And what is predicted is that the Kubo term has, so the mobility indeed has a phase transition. And so depending on whether the resistance is smaller than RQ or larger than RQ, this Kubo term will start vertically or horizontally. That's the phase transition. However, the superconducting, the inductive response here has no phase transition. In fact, it's not possible to have this inductive response vanishing with the compact phase because by symmetry and given that there is a confining potential here, it's very hard to imagine how this value of cosine could go to zero and vanish for value of the resistance that is larger than RQ. However, in non-superconducting systems, like the one considered by Kane and Fisher, there is no supercurrent, so the mean value of the cosine phi is zero, and then you can have this phase. I'm sorry, I clicked too frequently on my mouse so that I have uncontrolled jumps of my slides. Yes, so yes, so in non-superconducting system, you don't have this inductive response associated to the supercurrent. So cosine phi is mean value of the cosine phi is zero, and you have an extended phase. So with an extended phase, you can have I mean, you don't have this green contribution, so you do have the phase transition in this Kubo term. All right, so I'm almost getting to the end. So we started from this phase diagram, and we have shown experimentally that, in fact, we observed that the junction should be superconducting everywhere, and we argue that it should be superconducting everywhere. Nevertheless, the mean value of the cosine phi that gives us the strength of the supercurrent that can flow through the junction is not supposed to be the same everywhere. It may be very small in this region, and the junction will only be strictly insulating when EJ equals to zero, that is on this bottom axis. In this region of the parameters here, we have what we know as for the state of the Cooper pair box. So it's we can work these states exactly in this tie binding model for the charge states in the Cooper pair box, and we find that the reduced density matrix in the charge representation corresponds to an ensemble of charge states that are occupied simultaneously in the ground state. And in the phase representation, this reduced density matrix, we have some width associated to the width of this distribution of charge here. And we use a compact state, so it's periodic in phase. Now, if we increase the EJ over EC ratio, we still have another Cooper pair box. It's a transmon, if you want, and in the very large EG over EC, the envelope of these states here gets very broad, so you get in the end all this charge state will get evenly populated in the ground state, and the width of this phase here will become very narrow, so it becomes a Dirac peak. In this region, okay, the density matrix has the form of two Dirac combs, both in the charge representation and the phase representation. It's also similar in this region of the phase space, okay, but here it's because when you decrease dissipation here, you will allow more and more charge fluctuations. So in the end, you get also an equal representation of the charge states in the ground state of the system. Now, in this upper side of the system, in fact, the system is dual to the Cooper-Meyer box. Okay, and you can write more or less the same tight binding model, but for the Vanier states that are localized in the cosine, the different cosine waves of the Josephson junction. And if you are right at this boundary, so for R goes to 0, then you need to introduce the inductance of this loop in order for the system to make sense. So we have an extra inductive term. And you find that the solutions for this system are just the dual of this. So you would have a distribution of different Vanier states, and the charge states will get some weight here. Okay, so that's just the dual. So you have some duality line here that exchange the role of the phase and the charge in this phase diagram. So we don't know exactly what is going on in the middle here, but we expect to have some non-discrete charge in the junction, and also non-compact state for the phase. Okay, so that brings me to my conclusion. So the Josephson junctions do not become insulating when they are shunted by large resistances, and this clears paradoxes with respect to well-known limits. We argue that Schmid's prediction is valid in non-superconducting systems, but not for Josephson junction. And we propose a qualitative picture for the junction and its environment, which clarifies the phase compactness and the decompactification scheme for the phase. Of course, a comprehensive quantitative theory for the junction and its environment is still lacking, and we hope people will address this soon. Another thing that we can conclude is that when you obtain a quantum phase transition by mapping a normal state system onto a system with Josephson junction or other superconducting structure, then this may need to be reconsidered. For instance, there's a quantum phase transition predicted in 1D Josephson junction arrays, but recently Vladimir and his co-workers have observed that such arrays still behave as very good superconducting transmission lines, well above the predicted threshold for the insulating state of the array. Okay, and just before ending, I will thank my collaborators in this work, so many people in our Saclay group here, and we have also collaborated with theorists in Germany, so Armand Grabert from Freiburg University, and Jürgen Stolberger and Jacqueline Korod in the University of Ulm. And with that, I thank you for your attention.
Okay, thank you so much, Philippe, for very nice educational talk. Anyway, and thanks everyone for surviving through the connection imperfections. Let's take some questions. I have one, but if someone wants to go ahead, please.
Yes. This is Bill Phillips, Vlad, and Philippe. Thanks for that very nice talk. You began by describing a Josephson junction in the usual way as being two superconductors separated by an insulating layer, but there are other ways of making Josephson junctions, or at least things that people call Josephson junctions. You could put a normal conductor. You could, instead of an insulating layer, you could thin out the superconductor to make something that sometimes called a diam bridge. And what I'm wondering is, if you had these other kinds of Josephson junctions, how would this affect the story that you've told us?
I would say that our conclusion would still survive. I mean, there's no reason that a more general Josephson element, what you've described, a diam bridge or whatever, would become insulating by adding a resistor in parallel to it. If it doesn't work for a Josephson junction, what would it happen for another superconducting element? I mean, I could elaborate a bit more. If you consider another Josephson element, then you replace the first Josephson relation by something that is not the side of phi, which is a more complicated function. It's still periodic with the phase difference, but it's not harmonic anymore. But the rest of the story remains. You still have an inductive behavior, and this inductive behavior will not be damaged by the presence of a resistor. It will not be destroyed by the presence of a resistor.
Okay, thanks.
Charles Clark here. I haven't had time to figure out how to work out the connection, but there are a number of cold atom examples of Josephson-like circuits, and I'm just wondering if you've thought about any of those things, Philippe, and have some guidance as to how similar experiments might be done there.
I have thought about it, but not very precisely. I'm not at all an expert in cold atoms. I don't know if they know how to implement a resistance, for instance. I have no idea. So,
is Chris Lobb on the line? He might have some suggestions.
I mean,
I guess not.
If they can implement in some way something that behaves like a resistance, and what's really important is that you want dissipation to go all the way down to zero frequency. Otherwise, there is not even the question of having a phase transition. If the impedance that you present to the junction is not doesn't have a finite real part at zero frequency, then there is no chance it can give a dissipative transition. So if using cold atom they know how to implement this in some way, then they can try, and my guess is that they won't find any phase transition either.
Philippe, yeah.
Can I come in back, Vlad, or should I go after you?
Go ahead.
Okay, so I had a simple question and then a clarification question. So it was interesting that you have these distributions. We usually think of the phase as having a single blob, and you showed this extended phase plot. And so that's sort of the normal picture that we usually have for these qubits. Are you saying that some of the qubits sort of need to be reinterpreted? We should think of a different way in terms of compactification based on your research? So that's sort of my simple question. Maybe that's right. And then the other thing is, you showed discrete values of phase in one of your plots. You showed an overall phase distribution that sort of Gaussian-like, but it had all these finite peaks in it. A couple slides back, yeah, the upper right corner.
Yep.
And I was trying to figure out why the phase had discrete values there. If there's a reason why it couldn't, take on distribution of values for each peak.
So if you move in, so that's right on the boundary, and if you move inside the phase space here, yes, I expect to see something like that. So there's a distribution of phase, but so that's just by solving this simple model. And you have a discrete set of states at the beginning, and so discrete values, and that's just what it means. And we are doing this by analogy with what is working very well in superconducting qubits. That's all I can say. I mean, probing, if you have an idea to probe this distribution of phase and charge, it's very interesting. I don't know how to do that other than making the spectroscopy of a qubit or things like that. And if the spectroscopy agrees with the model, then what more can you say? How can you extract the weight of the distribution of the charge? I don't know. It's certain that this model with Dirac peaks is an idealization. You can think of it as just a very narrow peak. That's fine for me.
Okay, so there's no change in the Cooper pair box picture. Is that right?
No, and precisely that was one of our starting points. It's working so well. I mean, the agreement between experiment and theory in this region of phase space is so good that we have all the reasons to believe that this picture is excellent, and we have built up on that.
Okay, thank you.
Right. I actually have also a simple question. So you started at the beginning of the talk by saying that, well, if I take let's say a Cooper pair box or a Transmon qubit and shunt it by a very, very large resistance, obviously it shouldn't do anything to it, because thinking as a microwave engineer, it's just going to be an open circuit. Current cannot flow through it, so it shouldn't do nothing. But it looks like Schmid and Bulgadayev are saying that in some sense a Cooper pair box has to be an insulator in their picture. And I was wondering, is it really wrong to think of a Transmon or let's say a Cooper pair box qubit as an insulator? Because after all, if I look at the ground state of the wave function in phase, it is spread between 0 and 2 pi. And if I unfold it, like you described, into an extended representation, it will be just wave function everywhere, which is precisely what Schmid and Bulgadayev are saying, that you're going to get a possibility for the phase to be everywhere. Now, whether it's 0 to 2 pi or minus infinity to plus infinity, yeah, that could be a subtle question, but it doesn't look localized to a small region of values in the phase. Now, if I shunt Cooper per box with a 1 ohm resistance, well, I guess then it's hard to do an experiment, but presumably they're saying that then phase is going to be localized to, near zero, which is also fine. So yeah, I wonder what you.
So that's what I was saying. If you shunt a Cooper per box with a 1 ohm resistor, then you expect to see a very large distribution of charge states in the ground state and a very narrow phase peak. So we agree on that. So what you are saying is that maybe a Cooper per box is an insulating system after all. And in fact, we made an experiment in which we were sending AC current through a Cooper per box, and we could measure AC current flowing. So it's definitely not insulated.
Yes, but how do we define an insulator from, let's say again, microwave engineering viewpoint? So I would say that if its response in the zero frequency limit is like that of a capacitor, then I would be fine if I have to call it an insulator. And if on the other hand the response is inductive in the zero frequency limit, then I have to call it a superconductor. So that you can pass an AC current through it doesn't contradict that it's an insulator in that picture.
Yeah, but I mean, you can think of measuring precisely what's the admittance and see how it varies with frequency and know whether it's inductive or